Hello, this is Dr. Marina Sabra Jumail from the Lebanese University. In this chapter on PLCs, we are going to talk about timers and counters. We have different types of timers: delay on, delay off, retentive timers, and we are going to see what cascading timers is. And we have counters that count up, down, and up-down counters as well. So the basic function of time is either to delay an action to happen with respect to its input or to keep an output for a specific time. So we're going to talk about the different timer types. The timer on delay, or I'd rather call it the timer to become on delay. It's because the output is delayed with respect to the input when turning on. So as I just said, the timer is going to start counting when the enable turns on, but the output only turns on when the timer finishes counting. And here, this is a time chart that shows the action of the timer on delay. So this is the input, and once the input turns on, the timer starts counting during all this time. This is what we call the preset value of the timer. And once the timer finishes counting, the output is going to turn on, and it will stay on until the enable goes back off. When the enable goes off, it resets the timer. Therefore, it resets the output. It resets also the accumulated value. It goes back to 0. If the enable goes back to 0 before the timer done goes on, the timer also resets, so the accumulated value goes to 0, and whenever the enable goes back on, the timer should start counting all over again before turning the output on. I take an example on the kind of fridge that turns on a bell if you forget to close the door. So if I open the fridge, take a bottle of milk and put it back, and then I open it, even if I do that 10 times, 20 times, the alarm signal should not turn on, because the function demanded is I want to see if the fridge has been on in a continuous way for a certain amount of time. So this is the function of the delay on timer. Every time I close back the fridge, the timer resets and waits for another enable on to begin counting. This is in here the memory addressing that we already saw on the timer. This is the preset value, the accumulated value. So to address them, I have to put a dot, preset dot accumulated, because they are words and they are not bits. And I have the enable, timer timing, and done bits that I'm going to address with a slash enable slash timer timing or slash done. So in here, if the rung is true, so the enable bit is set, it's equal to 1, the timer timing is equal to 1, and the accumulated value starts counting whenever the enable bit goes to 1. When the rung is false, this means the enable bit has gone to 0 and the timer resets, so all the bits go back to 0 and the accumulated value is cleared, it doesn't begin counting. These are some examples of how we can see timers in PLC programs, ladder programs. So this is the enable and the reset bits that are two inputs to the block that we have in here, the timer. And within this block, we have the timer number, the time base. So the time base is the value that every step is going to count. It could be 1 second, it could be 10 seconds, it could be 0.1, 0.01, and the possibilities depend on the PLC you are working with. And this is in here the output and the inverted output. Another way to see a timer is like an ordinary output where we call it the timer's name, and this is the enable of the timer, and then in here we have the done bit or the output of the timer that is connected to the physical output of the PLC. This looks more like the one that you are going to see in the ladder program in the Rockwell, We have the enable connected to the timer block, and you can see here this is the enable line. The done, you can see its value, you can see if it is on or off, but you cannot connect it to anything. It's not physically connectable. What you are going to do is going to go back to another rung and call it. In Logic Explorer, instead of saying I12, what you are going to say in here, the index, you are going to say T40/timer timing for this line and timer done for this one, and you are going to energize outputs that are related to these. Delay off timer, or I'd rather call it delay to become off, is a timer that turns on with the enable and only turns off after it counts the preset value after the enable has gone back off. So this is the time chart. The enable has turned on, the output goes on with it, straightforward. When the enable goes off, that's the input to the timer timing starts counting, and when the timer timing finishes counting, the done bit goes back off. And of course, it doesn't need any reset because it has already reset it. The retentive timer, on the other hand, is a timer that memorizes the value of the accumulated. So whenever an enable goes on and then it goes back up very quickly, the value in the accumulated in here doesn't go to 0, doesn't reset. So it needs an external reset whenever you want to reset it. But on the other hand, if I have an application where instead of having the fridge open and close, I have a quantity of liquid that I am filling in a bucket, and I want the accumulated value altogether, even if it is interrupted, to become, let's say, 20 liters, I can do it with retentive timer. So this is an accumulated value of time that is being put together so that it turns an action on. Of course, it depends on your application. You can choose either one or the other. So in here, if I have the enable going on and off several times, if the sum of this time plus this time plus this one is the preset value, then the output will turn off. If it is a retentive delay on timer, then after the enable, when it goes down to off, the done bit goes also down to off. Cascading timers is important whenever I want to either accumulate two timers with different time bases, or I want to make a time delay that is larger than the timer permits. So the timer is limited to the maximum of 16 bits in its preset value, and this means that we can go up to 2 to the power 16 times the time base, and that's the time that we have. So 2 to the power 16, that's 65,000 and something. It's a large number, but when you want to talk about delays that go in like 10 hours, you cannot get a good resolution with timers with only one timer. So what we are going to do is we are going to allow a first timer to count, and when the first timer finishes counting, the output of the first timer is going to turn on the second timer. So when the first timer finishes counting, the second one begins, and therefore we have the sum of the different timers together, turning on the actual physical output. About counters, well, counters are going to count things instead of counting time in the case of timers. They can be up counters, down counters, or up-down counters. To be able to count objects, the counters are designed to count every time I have a glitch. So every time I have the input going from 0 to 1, I have a count. And whenever the count is equal to the preset value, the output turns on. So if the input, let's say I am counting bottles, and one bottle gets stuck in front of the sensor and I only see one large input value, the counter only counts once. If I have, sometimes the signal is large and sometimes the signal is thinner, so sometimes I have large objects and thin objects, the counter also counts each one once. Doesn't care about the time spent in the on level, neither the time spent in the off level. And this is very useful in industries when I want to count objects. The up counter counts upwards from 0 to 1. The application is that it counts finished products. And then when I have, let's say, 6 bottles, I want to wrap them together, so I can send the signal to wrap them together. The down counter on the opposite side counts, let's say, pieces in stock and the fact that they are decreasing. The up-down counter is very practical for whenever you have a vat or a batch and you have quantity of material coming inside and quantity of material coming outside, and you really want to know how much is there left within the batch. So you can, instead of using 2 counters and subtracting, just use an up-down counter with 2 different inputs. So this is the circuit of the up counter. So it looks like the timer with a preset accumulated value, the enable on the first line, and the done bit that you can see but cannot control. This is the done bit, and in here we have an overflow. Doesn't exist in all the PLC counters, and we have the reset because the counter cannot reset by itself. The same for a countdown counter. So in here the counter is going to count down from a preset value down to 0. Before I end the chapter, if I want to cascade timers, it's going to be the same as putting cascade counters. It's going to be 2 counters, one controlling the other, but in the case of counters, I can send control signals to finish one first, let's say, batch of 6 bottles, and then put them in boxes, and then finish a second batch of different sets of 6 bottles. So the cascading timers is also important for the control of machinery. That's it for this chapter. Thank you.